So, welcome to the 7th lecture of graph theory. So, today we will look at a notion called dominating sets. So, in the last few classes we had discussed about vertex cover, edge cover, etc. So we start from the vertex cover now. So, remember that vertex cover was a collection of vertices, subset of vertices such that all the edges are covered by those vertices. That means, at least one endpoint of each edge belongs to that set S. So, it is equivalent to, as we once mentioned, that if you have a graph, it is like finding out the minimum number of stars such that you get each edge in one of the stars, right. You can see it is like covering with the stars, right, minimum number of stars. Now, suppose I want to cover the number of vertices of the graph with the minimum number of stars, not necessarily the edges. For instance, let us look at a example. So, for instance, if I am talking about this graph, now you know what is the vertex cover of that. If I take this vertex, I cover this edge, this edge, this edge and this edge, but of course this edge and this edge is not covered. So, I will have to take this and this say. So, therefore, it is not possible to get a vertex cover by selecting only this vertex, but on the other hand, if I was interested to cover only the vertices, for instance in this graph, I am not bothered about the edges, but what I want is a collection S such that every vertex is a neighbor of it, right. So, here this is enough, because this is a neighbor of this is a neighbor of this is a neighbor of this. In other words, if I was looking for a collection of stars, star means a structure like this. So, such that all the vertices become part of at least one star, then we see we need only one star here. This covers all this thing, because these edges I am not bothered. So, this parameter is called the dominating set, and any dominating set which has the minimum cardinality is called minimum dominating set. Let us go to the formal definition of that. So, a set S subset of E of G is a dominating set if every vertex not in S has a neighbor in S. The domination number gamma of G is the minimum size of a dominating set in G. Now, if you look at these pictures, we can see that in all cases the dominating set need not be equal to the vertex cover. For there are several cases you have already seen. In some cases it can be equal, but there is no guarantee, right. And now, it looks like in most of these cases we drew the dominating number gamma of G seems to be less than equal to beta of G, but is it always true? Of course, it is not always true. For instance, you can consider a graph which consists of only isolated vertices. So, if you want to cover it with stars, so you have to take this all of them separately, right. So, while as far as the edges are concerned, there are no edges here. So, there is nothing to cover, or for instance, if you are considering a graph with an isolated vertex. So, with some isolated vertex here. So, for each of these isolated, you may have to take them separately, because nothing else can cover them in as far as a dominating set is concerned. But when we are looking for a vertex cover, because there are no edges between them, they are irrelevant. So, we will not even have to worry about them. So, therefore, in those cases the gamma of G, the domination number can be bigger than the vertex cover, the minimum vertex cover cardinality. So, but suppose there are no isolated vertices in the graph, then you can easily see that this inequality holds. Why? Because if you take a vertex cover that is indeed a dominating set also. It covers all the edges, and since every vertex has at least one edge incident on it, because we are assuming that there are no isolated vertex, either it is inside the dominating inside the vertex cover, so it is dominated already by the vertex cover, or it is outside and its edge, the other end point of the edge is in the vertex cover, right. Therefore, the vertex cover dominates all the vertices. So, therefore, vertex cover is indeed a dominating set provided there are no isolated. So, therefore, this inequality is always correct, but it does not mean that domination number has to be equal to the cardinality of the minimum vertex cover or very near to that. Sometimes it can be very small. So, compared to the cardinality of the minimum vertex cover. The extreme case happens when we consider the complete graph Kn. So, the gamma of Kn is just 1, as you can see, because if you just pick up one vertex, all other vertices are its neighbors. So, it dominates all of them. So, it needs only one vertex in the dominating set, while the vertex cover number beta of Kn, as we know, is n minus 1, because even if you drop 2 vertices from the vertex cover, so what will happen is there will be an edge between them and nobody will be there in the vertex cover to cover those things. So, therefore, in the case of complete graph, that gap can be very big. So, gamma can be much smaller than beta, that is what we are saying. The next thing is, so now let us look at some interesting observations about dominating set. The first thing is, if you have n vertices in the graph and the minimum degree of it is k, then we will always be able to get a dominating set of cardinality at most n into 1 plus log k plus 1 by k plus 1. This is what we are going to prove now. But before that, so can we say that there is some minimum value for the dominating set, say so some lower bound for the domination number. So, suppose the graph is say a maximum degree k graph. So, for instance, we can consider a maximum degree. So, delta of g equal to, so y k, let us say delta. Then you can say that any vertex if you pick up and add in the dominating set, it will dominate only delta neighbors and itself, together delta plus 1 vertices per vertex. So, but then there are n vertices to be covered, right. So, total n by delta plus 1 will be required at least. So, gamma has to be at least this much, right. So, this is an easy lower bound for dominating number in terms of this. Now, if it is a k regular graph, this becomes n by k plus 1. So, now come to the case of minimum degree k. So, of course, with respect to minimum degree you cannot say much, because minimum degree can be much smaller compared to the degree of most of the vertices, but you can get an upper bound interestingly. Like what we are going to do is this. So, we will show that. So, here is a strategy, greedy strategy. So, where we try to take the vertex which dominates the maximum number of all vertices which are not yet dominated. This is the strategy. In other words, we can suppose this is a graph, you can see which vertex has the maximum numbers as of now and pick this, and then you see this vertex added in the dominating set. So, this D, I will add it to D, and then all these vertices are already dominated. Now, you look at the remaining vertices. Now, from the graph we will see the biggest, I mean which vertex can dominate the biggest number of vertices from the vertices are not yet dominated, and then we can add that vertex to the set, and then in the remaining graph we will do the same trick like that, right. So, what do you do? So, how fast, how many times we will have to repeat this procedure is what we are going to consider now. So, this is the way we are going to approach it. Now, suppose you have a n vertex graph, and you already got some set S. So, you picked up some vertices and added to S. So, by our procedure say, and then this is that set S here, right. Now, this S dominates say this many vertices, let us say S dominates all these vertices, that means, so all these vertices are dominated by S. So, by some means for every vertex here you have a neighbor in S already. So, I am not bothered about these vertices now. So, what I am bothered about is this is the remaining vertices. So, let us say the remaining vertex set is U, the remaining undominated vertices as of now with respect to this S. So, my plan is to look for a vertex here which will get me maximum from this group, but then what if all of them are very bad? That means, what if say everyone dominates only one or something like that. So, which will not help me much, right. Every time you will add one more vertex, but then you will have to keep on doing this for maybe cardinality of few steps. So, because initial number of vertices, then you may end up with too much. So, but what we claim is that in this collection outside S, you will always find one vertex such that, so such that it dominates at least U into k plus 1 by n number of undominated vertices. Out of this U into k plus 1 by n factor of the U vertices which are undominated will be dominated by at least one vertex. So, that vertex we can add to S. So, which will be a reasonable portion of the undominated vertices. How do I show that? Suppose this is not true, that means every vertex x outside S is such that, so the number of vertices it dominates from U is less than cardinality of U into k plus 1 by n, strictly less than this. In that case, we will show a contradiction. So, I will to explain that is for the ease of explanation, I will do it like this. So, let us make a table. So, I will write down the number of vertices 1, 2, 3, 4 up to n here, and then I will put columns here for each of them. So, this is for the sake of explaining, and then so for each vertex from U, I will say U1, U2, U3, and this is U t, say t is equal to the cardinality of U. Now, we can draw some. Now, what we are going to do is to put a tick if U1 can dominate that vertex here. For instance, even if U1 dominates 2, I will put a tick here, even dominates 1, I will put a tick here. So, U1 may not be dominating 3, so I will not put. So, I like that I will put ticks. How many ticks will come in a row? You know that minimum degree is k. So, a tick will come corresponding to the on each of those squares in the column corresponding to its neighbors, and also for itself. For instance, U1 may be here itself, it will come because U1 dominates itself. So, k1 ticks definitely, at least, maybe more than that. Here also k1 ticks. So, like that. So, k1, similarly in each row we will have k1 ticks. So, if I count the total number of ticks, you see that there are at least U into k plus 1 ticks in it. Now, if you look at column wise, you see that if none of them, for instance, if you take any vertex from S, you won't see any tick here, because you know none of the u1, u2, u3 etc. can dominate the vertices from S, because there is no connection between them, right. While if you consider a vertex here, so if you consider a vertex here, so this vertex, because so how many ticks can be there in this thing, in a column, for instance in this column how many ticks can be there. So of course we have, by assumption we said that the there is each vertex x outside S is such that it dominates only less than u times k plus 1 by n vertices from u. So the number of ticks we see in that column will be less than cardinality of u into k plus 1 by n, right, strictly less than that. So this means that if you consider all the columns, total number of ticks will be, we can multiply by the number of columns, right, n columns are there. So we will only see strictly less than u into k plus 1 ticks, but we know that the number of ticks is more than equal to u into k plus 1, which is a contradiction. So what do we infer? We do have a column where there are at least u times k plus 1 by n number of ticks, or in other words there is a vertex outside S such that it can dominate at least k plus 1 vertices from u. So it can be inside u or not, can be inside u or not, does not matter. So we pick up that vertex and add to our set S. So if we start from an empty set and keep doing this thing, we will gradually reduce the set of undominated vertices. We will do it until the cardinality of the undominated vertices becomes less than equal to say n by k plus 1. There we stop, and then we add all the vertices in the remaining set into the dominating set, because they themselves dominate, each vertex in it dominates itself. So the total, suppose if we reach this situation in t steps, suppose if I reach this situation in say k steps, sorry p steps, so I will say p steps, then what can I say? So and I start from n, and after the first step how many vertices will be there in this u? U will become n into 1 minus k plus 1 by n, right. After the second step, so this is the first step, after the second step what we see is our u will become n into 1 minus k plus 1 by n into another 1 minus k plus 1 by n. Well, because this is the total number outside, we are taking away this fraction of that. So into this thing, this will become n into 1 minus k plus 1 by n to the power 2. So after p stages, we will see n into 1 minus k plus 1 by n to the power p undominated, still undominated vertices. So suppose I want this to be less than equal to n by k plus 1, then how big should be the p should be, how much p should be, how big should p be? So we cancel this thing. So we can say that this is an so for instance I can always say that 1 minus x is less than equal to e raised to minus x. It's a well known inequality. So what I want is 1 minus k plus 1 by n to the power p to be less than something. So I know that this is less than, so by using this inequality I can write this is less than e to the power minus k plus 1 by n into p. Say if this itself is less than equal to k plus 1 by n, then of course sorry less than equal to not k plus 1 by n, 1 by k plus 1. So, we dropped n of course when we cancelled n from both sides. So, then we see that so we can add the rest of the things as such, right. So, what will the value of p be? So, you can take, so think of substituting p with n into n by k plus 1 into log k plus 1. So, what will happen? This n1 will cancel this, and this k plus 1 will cancel this, log k plus 1 minus will become 1 by k plus 1 less than equal to. So, this will be true. So, if you take p to be greater than or equal to n by k plus 1 into log, sorry this log, I should put this log because this log is with respect to natural logarithm k plus 1, then we see that this will become less than 10. So, now along with this p vertices, we also have to add the remaining n by k plus 1 vertices. That means, I need p plus the final size of the dominating set is this much, that is equal to n or less than equal to, I can say I can take n by k plus 1 into log of k plus 1 plus 1. So, this is what we get, a dominating set like this. This is a greedy algorithm. So, which produced a dominating set of cardinality this much. So, therefore, the statement of the theorem. So, this is what the statement of the theorem. So, this sized dominating set will come if the minimum degree of a graph is this much. Now, so we can talk of various kinds of dominating sets, variations of this dominating set problem by adding some additional constraint about the dominating set that we get. For instance, we can ask that is it possible to get a dominating set which is connected? Of course, we can get it, but the only thing is that if you look for the minimum cardinality, the cardinality of the connected dominating set. So, of course, the graph has to be connected then, right. So, will be definitely more than equal to the dominating set, because the connected dominating set itself is a dominating set. So, the condition for connected dominating set is you just say that it is not only a dominating set, the induced subgraph on the dominating set is connected. So, another kind of dominating set is independent dominating set, which is, so when we require that the dominating induced subgraph on the dominating set is an independent set, then it is called an independent dominating set. Now, there is something called a total dominating set, where we require that there are no isolated vertices in the dominating set. Okay, fine. Let us look at this independent dominating set and see an interesting statement about it. So, the independent dominating set, I mentioned that independent dominating set is actually a dominating set whose cardinality is, sorry, whose induced subgraph is independent. Now, I can say that it is essentially a maximal independent set. What does it mean? So, maximal independent set means it is an independent set, but not any independent set will be a dominating set. So, you can for instance take an independent set and then suppose you can add one more vertex to it, add, that means if there is no edge between this set and this outside vertex, then you can always add it and you will get a bigger independent set. You keep adding it and finally, you will reach a situation that you cannot add any more vertices to it and make it bigger, from any more outside vertices to it and make it bigger. Why is it so? Because any vertex outside, if you take, they will have at least one connection into this independent set. If you try to pull it into the independent, there will be a conflict. So, this kind of independent sets are called maximal independent set. So, it is not necessary that a maximal independent set is a maximum independent set. So, the maximal only means that you cannot given this set independent set, you cannot add one more to it and make it bigger. So, there is no other independent set such that that is a superset of this, but maximum means cardinality wise it should be the biggest. So, you can always talk about other notions like minimal vertex cover. So, a vertex cover we have discussed about the minimum cardinality vertex cover, but suppose if a vertex cover is such that if none of its proper subsets are vertex covers of the graph, then we call that it is a minimal vertex cover. So, it need not be cardinality wise minimum. So, there are these words minimal, maximal, which we usually use in graph theory. So, we have already used in the context of the proof of Tutt's theorem this word edge maximal graph like that. So, now we claim that this maximal independent sets are dominating sets. Why? Because you see any other vertex outside, so it should have an edge into that. It is so this independent set is dominating the outside, all the outside vertices. So, therefore, it is a dominating set. Now, again if the dominating set is an independent set, so it is indeed a maximal independent set. Why? Because you take the dominating set, any outside vertex should have an edge into that because it is a dominating set. So, therefore, you cannot move any outside vertex into it, because then conflict will come. So, it means that the maximal independent sets are indeed the dominating sets that have that give us an independent set and induced subgraph, independent dominating sets. Now, we will look at an interesting statement about the independent dominating sets. So, it says every Clawfree graph has an independent dominating set of size gamma of g. That means, gamma of g, remember it is the cardinality of the minimum dominating set without any constraint. So, of course, if you are asking for independent dominating sets, even if you take the minimum, it has to be of cardinality at least as much as gamma of g. There is no guarantee that in the general case you may get an independent dominating set whose cardinality is gamma of g. But I say if you take a class of graphs called Clawfree graphs, then you will always get the independent set, an independent set which is also a dominating set such that its cardinality is indeed equal to gamma of g, that is the cardinality of the minimum dominating set. So, why is it possible? Before that I have to explain what is a Clawfree graph. So, first for that you should understand what a claw is. Suppose in a graph you see a vertex like this and you see at least 3 edges going out of it, suppose 3 edges going out of it such that here this edge is missing, this edge is missing and this edge is also missing, and this is called a claw. There can be many other things in the graph. I am just taking this vertex and 3 of its neighbors, and if it so happens that these 3 of its neighbors are independent, that means they do not have any edge between them, then this is the entire star, this 3 star, right. So, this setup is called, this structure is called a claw, and if the graph does not have any claw in it, then it is called a Clawfree graph, then it is called a Clawfree graph. So, we claim now that if you give me a Clawfree graph, then the cardinality of this minimum independent dominating set will be equal to gamma of g, the cardinality of the minimum dominating itself set itself, or in other words we will be able to find a minimum dominating set which gives me an independent set as induced subgraph with the cardinality gamma of g. So, how do I prove this? So, now because it is trivial to see that any in any independent dominating set should have cardinality greater than or equal to gamma of g. So, we just have to show that. So, here is an independent dominating set whose cardinality is less than or equal to gamma of g. So, to do this thing, just first consider a dominating set minimum dominating set. Let us say this is the minimum dominating set. So, what does it mean? This will the remaining part I will draw like this. This is the remaining part. So, I am instead of which essentially means that any vertex here will have a edge back to this. Any vertex in this side will be connected to this. Now, there is no guarantee that this is an independent set. There can be some edges inside this. Now, what we do is we will look for some maximal independent set here, some maximal independent set here. So, let us say this is the maximal independent set. So, this be called S. So, what is the meaning of this? Because in this part, in this induced subgraph, this S is a maximal independent set. This is a dominating set of this. Of course, this dominates all the vertices of this, but of course, this won't dominate all the vertices here, because if it dominates all the vertices here also, then S itself is a dominating set, and then smaller than this one. So, which will be a contradiction to the assumption that this is a minimum dominating set. So, or unless this S itself is a independent set, S itself is equal to this, which means whatever we are looking for we already got. We only wanted to demonstrate an independent dominating set. So, now let us say, so we should assume that, so here only this S can definitely dominate all the vertices in this part, but it will be able to dominate only a little bit from this side. So, let us say it dominates, it is able to dominate this much. So, this is the remaining part which is not dominated by S. So, what we do now is to pick up a maximal independent set in this part, in this induced subgraph. In this induced subgraph, we will pick up a maximum dominating set. Let this be called T. Now, one thing we can immediately observe is S union T is independent, is an independent set, is an independent set. Why is it so? Because this is an independent set, this is an independent set. There is no edge between this and this. Because you see, in that case, we would have put this thing here in this group, right. So, there is it's S and T together is an independent set, easy to observe. Now, the next thing what we can observe immediately is that together S and T dominate all the vertices, because S dominates all these vertices and all these vertices, while T, because it is a maximal independent set in this part, it dominates all the vertices in this part, right. Maximal independent set dominates here, right. So, this entire graph is dominated by S union T. So, what we have now shown is S union T is independent and dominating. So, it is indeed a independent dominating set. So, the only thing to show now, this S union T, the independent dominating set we have shown, is less than equal to the cardinality of the so less than equal to gamma of G, right. This is all we need to show. But to go back, the gamma of G is essentially, see, the cardinality of this set, right. Let me redraw it here, the next page. So, we have, this is the gamma of G. So, we have the S here. So, now we are interested in what is the gamma of G minus the cardinality of S. That is essentially the cardinality of this, right, this one, this set. So, this set, now you can say, for instance, the minimum dominating set is A. So, this is the cardinality of A minus S is what we are interested in, the A minus S. Now, on the other hand, our T was, so this much was already dominated by S, right. So, this was already dominated by S. So, here T was a maximal independent set T, and this dominates all the vertices in this part, So, if it so happen, we have to show that A minus S cardinality is greater than or equal to cardinality of T. In that case, S plus T will be definitely less than S plus A minus S, that is A. So, it will be less than equal to gamma of G, because cardinality of A is indeed the gamma of G. We need to show that this cardinality, the cardinality of this set, is less than equal to the cardinality of this portion. How do we do that? See, suppose this is smaller. Suppose there are k vertices here and there are, say, k plus 1 or more vertices here, k plus 1 or more. Then you know that there is at least one vertex here, because this set has to dominate this entire thing, because S, none of the vertices in S has any connection to this portion. So, these k plus 1 vertices, k plus 1 or more vertices has to be dominated by these k vertices. So, there should be at least one vertex here which has two neighbors into this, right, two different neighbors, because all of them, if all these k vertices are only one neighbor in this, so then how can they dominate k plus 1 vertices? By pigeonhole principle, there should be at least two neighbors for at least one vertex here. So, let this vertex be called Z. Z has two neighbors here, and because S is a maximal independent set, so there should be a vertex which is in S, which is a neighbor of this. There should be an edge like this into S. Otherwise, I would have pushed Z into S and told that S is not a maximal dominating set. So, this set has one neighbor in this, one neighbor here and one neighbor here, and you know that this together with this is an independent set. So, it is so it so happens that we have a claw here. This set has three neighbors which are independent, right. So, it is a claw. So, but then originally we told that the graph is claw free, so it is a contradiction, therefore, this set will give you a contradiction. So, we infer that in a claw free graph we should get an independent dominating set, here S union T, such that its cardinality is equal to gamma of G. This is the inference. So, this is, so we will wind up the dominating set with this. And now, so the next topic we are going to consider is another kind of cover called path covers. Let us say this, here is a simple statement. In a directed, so suppose if you take an undirected graph and then suppose I make this statement that I can find a path cover in it whose cardinality is less than equal to the maximum independent set. So, what do I mean by that? So, you can, so first you have to say what is a path cover. So, you can say that it is a collection of paths such that it covers all the vertices. For instance, if you take this graph, now you can say that this is a path cover. So, this is this path and this path, say this singleton path, they cover all the vertices, right. So, I take this path and I take this path and I take this path. So, it is a collection, a set of paths such that they are disjoint, that they do not share any vertices, and then together the union of their vertex sets will give you the vertex set of the graph. Now, look at this statement. So, I am interested to get the minimum number of the minimum cardinality of a path cover, and we say that this minimum cardinality of the path cover is less than equal to the maximum independent set size of the graph. So, we can check it in create some examples and do that. For instance, if you look at a complete graph, so this is one case where the independent set, maximum independent set is quite small. So the alpha of G here is equal to 1. So do we get a path cover of this with cardinality of path cover with number of paths in it, right? So number of paths in it just 1, because 0 is not possible. So of course you can get a path, a Hamiltonian path. If you have a Hamiltonian path, then definitely we know that the path cover is the cardinality of the path cover is 1, because that just one path is enough in the, so that's enough, right? So for instance, if you take a star, in a star, you see, you can, once you take this edge, because this is the biggest path you can take, right, 1, 2, right, not more than this. So you cannot come back. So now 3 vertices are gone. All other vertices you have to take as this trivial paths, 1, 2, 3, 4, 5. So in a star Sn, so for instance, in a, if there are n minus 1 hands, then what you get is n minus 3 plus 1 is equal to n minus 2 is the number of paths in the best path cover, in the minimum path cover. Now you can see, so this the independent set, but is n minus 1. So this is still less than equal to the biggest independent set, alpha of G. So by from some observation we see that this is always correct, but this statement is very trivial proof in the undirected case. So for instance, so what I have to show is that if you give me the minimum path cover, then I can show a independent set of cardinality at least as much as the number of paths in the path cover. So you can consider this path cover. So you take one path cover. So this, maybe this can be the path cover of the graph. Now you claim that this is minimum. Now I will show you an independent set from this thing, such that I'll be able to place one vertex in each of the paths and say that that collection of vertices I have picked up by placing one vertex in each of the path is an independent set. So therefore the cardinality of this will be less than equal to the, in particular, the biggest independent set cardinality. So this is the way to pick up. You take the n points of this thing. Now you can see that it is obviously 1, 2. So this is an independent set. Why? Because suppose if there is an edge like this, suppose, then we would have taken a longer path like this, right? And then what will happen? The minimum path cover will be even smaller, right? So the argument, the assumption that what we got was the minimum path cover is wrong. So therefore this edges, this kind of edges cannot be there. So by just picking the n vertices of the path cover, we will get an independent set. So in a directed graph, the statement seems to be very easy, but more a non-trivial statement can be made. That means if you consider an direct, so we are talking about undirected graph here up to now. So when we consider a directed graph, and then also this statement is true, but in a directed graph, what is the path cover? So the paths now are directed paths. The paths now are directed paths. So for instance, I can consider this graph. Say, so here I will mark some path cover. So this is a path cover here. It is a directed path, right? Here also this is a path cover. So all the vertices are covered by two disjoint paths here. Or I could have marked another path cover, like I could have taken this path. And then this single vertex path. So this is another path cover. So, here it is the path cover concept is the same as in the undirected case, but just that this time we have to take directed paths. So, if you say that x 1, x 2, x 3, x k are the paths, then there should be an arrow from is a path, then there should be an arrow from x to x like this. Now, we are again interested in the minimum cardinality of the path cover. So, again the question, is it possible that the minimum cardinality of a path cover is still less than equal to alpha of g? See, from it you should understand that when you consider an undirected graph, so there are several possible ways of orienting its edges. So, some method of orientation, some way of orientation, orienting the edges, when we give the edges some directions, it is possible that the path cover size may increase drastically. Well, let me see. So, for instance, you look at the simple graph, this is a path. In this the undirected graph, the path cover is just 1 because this is long path. But suppose I orient the edges of this graph and make it a directed graph by doing this. Now, what is the path cover? For instance, if I try to go from here to here, you get stuck because the direction here is in the wrong way. In whichever way I go, I can take only one edge here. That means one path covers only 2 vertices here. So, the best thing I may be able to do is to take this and then take this, right, take this like that. So, maybe n by 2 is the best thing that you can get. So, but you can see that in the undirected case the minimum path cover cardinality was 1 and it went to n by 2 depending on even or odd, right. So, if it is a even number, you can make it n by 2 exactly, otherwise I guess you will need one more. But this is a big increase, but even then you can see that the independent set size here is still greater than or equal to this the minimum cardinality of the path cover, or in other words the minimum cardinality of the path cover even after directing like this remained less than equal to alpha of g. So, the question, is it possible that in the directed case also this statement is true? So, we can, before getting into that, we can just check for some field, we can check in the bipartite case. So, on special case, so this is a bipartite graph. So, this is A side and this is B side. Suppose I orient all the edges from A side to B side. So, edges are always going to the A side to B side. Now, I ask what is the cardinality or the minimum path cover here. Of course, if you want to minimize the path cover, the best strategy would be to take the longest paths possible, but then here any path can be at most 1, the length of any path, any path can be 1 or 2. 1 means it is a single vertex path, 2 means it is an edge. So, you cannot, once you go like this, you cannot go further because it is a bipartite graph. So, you have to go back, but then always the edges are oriented from A to B. So, I guess if you want to minimize the number of paths in the path cover, the best strategy would be to take as many number of 2 length paths, 2 vertex paths as possible, and a 2 vertex path is an edge and they have to be disjoint. Therefore, we are looking for the maximum matching that is alpha dash of g plus the remaining, right. For remaining vertex, each of them will need 1. So, how much is remaining? N minus 2 times alpha dash of g. So, what is the cardinality of the minimum path cover here? So, that is of case n into alpha dash of 2 alpha dash of g plus alpha dash of g is essentially n minus alpha dash of g, n minus alpha dash of g. This is the cardinality. Why? But then is it less than equal to alpha dash alpha of g? So, in the independent set size, this is alpha dash of g, the biggest matching. So, but this alpha of g is, I know that it is equal to n minus beta of g, the vertex cover, and this is actually n minus alpha dash of g also, because this by Koenig's theorem, this and this are same, the biggest matching and the smallest vertex cover have the same cardinality. And as I have seen earlier, this quantity is exactly the cardinality of the path cover. Therefore, we end up in the bipartite case, it just touches the upper bound we are looking for. That means it is equal to alpha of g. It is equal to alpha of g when we orient all the edges from A side to B side. So, but so now it looks like an interesting question. Probably there are some graphs whose minimum path cover cardinality can be more than alpha of g, but in the next theorem we will see that it's not possible. So, always the minimum path cover cardinality in a directed graph is at most the independent set. Not only that, a little more than that. We have seen that in the undirected case, we could make an independent set from the paths in the minimum path cover by picking up the n vertices of each path, the terminal vertices, that is what we call usually. The last vertex of the path is the terminal vertex. The picking up the terminal vertex of each path, we proved that that is going to form an independent set. So, now we say that, but in the directed case, there is no guarantee that if we pick up the last vertices of each path, they are going to form an independent set. Because see, you can look at this example. So, for instance, if I see a directed path, so this is the directed path and this is another directed path in the path cover. Now, you can have an arrow here, right. So, you can indeed have an arrow here. So, we cannot say that I will, like in the earlier case what we told is, so I would have taken this longer path, but then now this is in the wrong direction because the arrow is in the wrong direction. So, if in both ways you cannot go like this, and then that is not a directed path. So, therefore, that argument does not work here in this case. So, it's so by picking up the last vertices, which we call the terminal vertices of each path, we cannot get an independent set. But our theorem says that okay, need not be the last vertex, but you can always pick up, there will be one vertex from each path, so that if you put them together you will indeed get an independent set. There is a set Vp, P element of P of vertices, such that this Vp is coming, it is a vertex from P, right. So, each path will contribute a vertex and together they will make an independent set. Together they will make an independent set. This is what it says. Now, to prove this thing, we need some concepts. The first concept is, we are interested in the minimum path cover, but let us say if suppose somebody gave us a path cover. So, this is a path cover for the given graph, directed graph here. So, here directions are there. So, these vertices, as I told, these are the terminal vertices, this set. So, suppose this P is the path cover and this is P1, P2, P3 etc. the paths in it. These are all the paths in it, the set of paths. and these vertices, say let us say these vertices, this set is called term of P, that is the terminal vertices of P. That means we pick up the n vertices of each path from P, and then that set is called term of P. And now we define a concept of minimal path cover. See, this minimal path cover is not like, so for instance, I give you a path cover, I will not say that it is a minimal path cover if no proper subset of it is a path cover of the graph. That is not the way to say, because any proper subset will not even be a path cover. For any path cover, that will be true, because give me any path cover, if you remove one path from that, the remaining thing is not going to cover the entire all the vertices in the graph. Therefore, that is not the way. So, we will define it with respect to the set term of P. So, the minimal path cover, if P is a minimal path cover of this directed graph G, if there exists no other path cover, say P1 of G, such that term of P1 is a proper subset of term of P. That means, we cannot get another path cover in the graph such that its set of terminal vertices is a proper subset of the terminal vertices of this path cover. So, there can be the possibility, there is a possibility that this path cover P, which we call minimal, is not a minimum path cover. It may not be cardinality wise minimum, but just that we have to make sure that there is no other path cover with their vertices, n vertices of the paths is a proper subset of the n vertices of this paths in this set. But on the other hand, we can clearly say that any minimum path cover has to be a minimal path cover also, because if there is any other path cover with the terminal set, a proper subset of this, that path cover is going to be of smaller cardinality, because the cardinality of the terminal vertex set is equal to the cardinality of the path cover itself. So, therefore, it is not possible, because if our one is minimum path cover. So, minimum path covers are minimal path covers, but not the other way. There can be minimal path covers which are not minimum. Now, our proof will say that you give me a minimal path cover, then we will be able to find an independent set such that there is a representative from each path in the from that. So, we will from each path of the path cover. That is what we will give the proof of this in the next class.